Good afternoon. My name is Jaryd Domine. I'm from Tarleton State University, and over the past year I've been working on a multidisciplinary project trying to make truss structures lighter and cheaper. A truss is made of a framework of beams connected at nodes, and the most common truss to us is probably the power transmission tower. There are about 27 million power transmission towers in the United States alone, and they cost $10,000 to $100,000 each. That's mostly in material costs. Now what we're doing is called truss sizing optimization. We are resizing each of the beams in a structure to make it as light and inexpensive as possible without sacrificing its structural integrity. This type of optimization has been used to great effect in large-scale projects where even the smallest change in weight can mean millions of dollars saved. So we would like to use less material, but there has to be a limit. And this is the key dilemma. Thicker beams are stronger, but they're also heavier and they weigh more heavily on the beams below them. While thinner beams are cheaper, that's what we want. And this conflict gives us an optimization problem. We want to find this happy middle ground of strong and cheap. Now the method we've come up with for doing this is based on our muscles. So if you work out your muscles, they grow. If you don't use them for a while, they atrophy. So let's say we have two beams under different weights. The beam on the left isn't under much strain, so we will make it thinner to save money. The beam on the right, we will make thicker to better support the weight that it's under. Now, most of the algorithms in use today can only handle static loads that don't change over time, but ours is built into a physical in-body simulation, which means we can use dynamic loads. And this opens us up to a whole realm of modern applications, like 3D printed parts or vehicle chassis. So let's see it in action. In this structure, the red beam is being heavily compressed, and we see that over time, it thickens while the other beams get thinner. So it has redistributed its weight. Now we have modeled many structures, but here's a simple one. This tower shows off our ability to handle dynamic loads. It is being shaken in an earthquake. It also has 6 cable loads at the 6 points. And as we see over time, the vibration dampens out. Our most recent breakthrough has been to parallelize this program, which means we can run many simulations at once and receive results much more quickly. We are also currently working on a paper with Dr. Wyatt and Dr. Rajesh Vedandam, which we hope to have published within the next year. Thank you for your time. I hope you enjoy this and other talks. Please let me know if you have any questions.